Welcome back to the deep dive. Today, we're really getting into some intricate stuff the decision-making dentists face when dealing with a tooth that's well compromised.
It's definitely not straightforward.
Right. It's more than just filling a hole. We're talking structural mechanics, how forces spread out, basically how to make this tiny stressed part of the body resilient again.
Exactly. And when you're looking at restoring a tooth, there are really three big things to balance. First, the mechanical side, can it actually take the chewing forces, without breaking?
Okay, the big one.
Then there's the biological aspect. How much healthy tooth can we actually save? And of course, the aesthetics, how it looks.
Makes sense.
But today, we're focusing mainly on that mechanical challenge. How do you navigate that line between keeping the structure stable and, well, preventing failure?
Okay, so let's unpack that. Our goal here is to walk through the 6 main ways dentists reinforce teeth. We've got this acronym SMARTE to help keep track.
Ah, yes, SMARTE.
These 6 methods, they're like a gradient, right? Starting small, preserving what you can, and scaling up the intervention as needed.
Precisely. It covers structure preservation, monoblock buildup, addition of fibers, removal of weak cusps, which is capping, total capping, and finally encircling axial walls.
Got it.
And to really get why a dentist might choose, say, adding fibers over just preserving, you first need to appreciate how incredibly well-designed a healthy tooth actually is.
That's the starting point then, the biomechanics. How does a healthy tooth handle all that stress?
Well, the fascinating thing is its natural architecture. It's essentially based on an arch or a dome shape.
Like an engineer designed it?
Pretty much.
Yeah.
And the forces involved are honestly quite significant. Think about the side-to-side horizontal forces, maybe on flatter surfaces. Those are around, say, 2 to 4 kilograms.
Okay, manageable. But what about the main biting force down onto those cusps, those little domes?
That's where it ramps up significantly. We're talking vertical forces often hitting 6 to 8 kilograms. And that dome shape, it's perfectly adapted to take that vertical load and convert it mostly into compressive forces.
Compressive, meaning pushing together.
Exactly. It distributes the stress widely, pushing the components together throughout the whole structure. That's what gives it resilience.
So compression is good. What's the bad guy then? Tension.
Tension is the primary enemy, yes. Unlike compression, which spreads out, tension concentrates strain. It pulls things apart, usually right at the weakest points, often the height of contour.
Okay.
So the health of the tooth really hinges on structural continuity. Imagine the ridges and grooves connecting the cusps, like a series of interconnected arches or maybe a suspension bridge.
Right, it needs to be whole.
That continuity is what lets it absorb stress elastically and transfer it broadly.
And when decay, or maybe an old filling, breaks that connection, breaks the bridge, so to speak.
That's when you get structural discontinuity. The network fails. Stress can't flow anymore.
So it gets stuck.
It concentrates, usually right at the base of whatever structure is left standing but unsupported. That part then acts like a pivot. And that stress concentration, that's what leads to the tiny cracks and eventually the fractures we see clinically.
Okay, that really sets the stage. So we go from the ideal blueprint to the reality of damage. And the core decision metric is comparing the force being applied, let's call it F.
Right. The patient's bite force.
Versus the tooth's remaining resistance, R.
F versus R. That's the calculation. And we start with the best case scenario, where the tooth is still holding its own.
Case 1, the cavity's small, resistance is high. F is much less than R.
Absolutely. In this situation, you don't need any extra reinforcement. The goal is pure structural preservation.
Just keep what's good.
Exactly. Save every bit of healthy enamel and dentin you can. It's interesting, this principle holds true elsewhere too, like with veneers. If you preserve the enamel during prep, the bond is way stronger and they last much longer, often over 15 years.
Makes sense. Less is more sometimes.
So method 1, structured preservation. Keep it simple if possible.
But reality often isn't that simple, especially with bigger cavities or old fillings failing. What about when things are more balanced? F equals R.
The tipping point. Now we need to do something specific to help that resistance. And the big threat here isn't just the chewing force from outside.
Oh. What?
It's the stress from the inside, from the filling material itself as it sets what we call polymerization shrinkage.
The filling shrinks as it hardens.
Right. And as it pulls inward, it can actually put stress on the remaining, possibly already weakened walls of the tooth. It can even cause fractures itself.
So the solution needs to fight that internal stress, too.
Precisely. And that brings us to SMART method 2, the monoblock buildup.
Monoblock, meaning one solid piece.
Essentially, yes. You need a really high-quality adhesive restoration, bonded perfectly, with no voids. It needs to act as a single, unified block with the tooth.
How do you achieve that?
It demands meticulous bonding. Whether you use etch and rinse or self-etch systems, the absolute key is creating a perfect hybrid layer.
The hybrid layer. Can you quickly explain what that is for our listeners? Why is it so vital for this monoblock idea?
Think of it like the ultimate handshake between the filling and the tooth dentin. It's a microscopic zone where the adhesive actually seeps into and interlocks with the demineralized tooth structure.
Like microscopic Velcro.
That's a great way to put it. If that layer fails, the seal breaks down, fluids get in, and the whole restoration is compromised. The monoblock technique is all about creating that seamless, continuous bond to resist the shrinkage forces.
Okay, so we've covered preserving the best bits and then carefully bonding when things are balanced. Now we move into more serious territory. The tooth structure is clearly struggling. F is definitely greater than R. A simple filling won't cut it.
No, definitely not. Just putting more composite into a structure that's already failing doesn't fix the underlying mechanics. It'll just break again.
So you need to actively strengthen it.
You have to boost the internal strength. And that leads us to method 3, addition of reinforcing fibers.
Fibers, like rebar and concrete. What are these made of?
Exactly like rebar. Usually they're glass or polyethylene fibers.
Oh.
And they dramatically change the composite's properties.
How so?
Well, they give the final restoration a much higher elastic modulus. That means it's stiffer, less likely to bend or deform under load. Plus, they really help combat those internal shrinkage stresses we talked about.
Ah, okay.
They create what's sometimes called a stress-free interface inside the filling, significantly boosting its resistance to the constant pounding of chewing forces over time.
So internal scaffolding. Makes sense. But what if the damage goes beyond just needing internal support? What if the edges, the cusps themselves, are weak or cracked? The rebar won't stop the whole wall from collapsing, right?
The next critical point. If the rim of the tooth, the occlusal rim, is broken or you've lost a marginal ridge, a cusp might become isolated.
Isolated and weak.
Exactly. It's prone to cuspal tipping. Internal fibers alone won't prevent that cusp from flexing or breaking off under load.
So what's the move then?
This leads to the next intervention, which can seem a bit counterintuitive at first. Method 4, cusp capping, which often involves the removal of weak cusps.
Hold on. You remove more tooth structure to save the tooth? That sounds drastic.
It is a calculated removal, yes. But think about the mechanics, the leverage. A tall, isolated cusp acts like a lever when force hits it.
Okay, I see.
It applies a really damaging sideways or tipping force at the base. By capping that cusp, essentially reducing its height and reshaping it, we do two crucial things.
Which are?
First, you shorten that damaging lever arm. Less leverage means less tipping force. Second, you fundamentally change how the force is directed.
Ow.
You convert those harmful lateral forces back into mainly compressive forces, directed down the long axis of the tooth into its stronger core, just like the original dome design intended.
Ah, so you're basically recreating the dome principle, redirecting forces back to compression. That's clever. Biomimicry in action.
Precisely. It's about managing leverage and stress direction.
Okay, we've gone from simple fills to advanced bonding, internal reinforcement, and now strategic reduction. We must be getting close to the most severe cases, the badly compromised tooth, or BCT.
Yes, this is where the structural loss is really significant. The risk of the whole tooth splitting vertically or wedging apart becomes very real. We're talking forces that might be double or even more than what the remaining tooth can handle. F is way greater than R, maybe even F2R.
So what's left? Full coverage?
Essentially, yes. We need something to cover and hold everything together. This brings us to method 5, total capping. This category includes things like traditional crowns, but also endocrowns and large onlays or overlays.
Now, this is where it gets really interesting, especially comparing crowns versus onlays. The data you mentioned earlier about strength loss is, well, it's pretty eye-opening.
It really is, and it highlights a fundamental trade-off. A traditional full crown preparation requires removing the tooth's natural bulge, the height of contour.
That protective curve we talked about.
Exactly. That area is key for handling compressive forces. When you remove it to prepare for a crown, the stress doesn't get distributed nicely anymore. Instead, the maximum force gets concentrated right down near the gum line at the cervical area.
And the consequence of that shift in stress?
It's huge. Studies suggest removing that height of contour for a crown prep results in about a 75% loss of the tooth's original structural strength. 75%.
Wow. Compared to...
compared to a well-designed onlay or overlay.
Hmm.
Because those preserve more of that critical height of contour and manage forces differently, the strength loss is estimated to be much lower, maybe around 35%.
That's a massive difference, 40 percentage points, especially when the tooth is already weak.
It's enormous.
Yeah.
So while crown provides full coverage, it comes at a significant mechanical and potentially biological cost to what's left underneath.
So the more conservative option, like an onlay, is often mechanically superior if you can make it work.
Generally, yes, in the long run. There are other options too, like the endocrown you mentioned. It uses the pulp chamber inside the tooth for retention, often in root canal teeth. It replaces lost dentin with stiff ceramic.
Sounds strong. Any downsides?
It can be very effective,
Yeah.
but there's an inherent risk. Because it sits inside the tooth, it can potentially create a wedging effect, pushing the remaining walls outwards. This could increase the risk of fracture from the inside, ironically.
Okay, complex trade-offs everywhere. So that brings us to the final stage. What if the tooth is just incredibly badly damaged, almost nothing left, maybe no marginal ridges at all?
Right, a true structural remnant. This situation forces our hand to the final SMARTE method, encircling axial walls. This is typically done with overlays, either made indirectly in a lab or sometimes directly.
Encircling, like putting a band around it.
Pretty much. Because there's so little tooth left for retention, you have to prepare it differently. You need significant reduction of the biting surface, and you also have to reduce any remaining height of contour. To allow the restoration, the overlay, to physically wrap around and encircle what's left of the axial walls, it needs to both bond and physically contain the remaining structure. The restoration itself is now providing almost all the structural integrity.
So looking back at all 6 methods, SMARTE. It's not just picking one treatment. It's a clear progression, isn't it? A gradient of intervention based on that FVSR calculation.
That's the core idea. It's a calculated response.
Yeah.
Every step up in intervention from S to E is justified by the increasing structural compromise and the need to restore or maintain that vital structural continuity.
Continuity is key.
It's the tooth's main defense against those relentless chewing forces. We're always trying to manage the forces, minimize the bad lateral ones, maximize the good compressive ones.
And once the restoration is done, how do you judge success? How do you know if the reinforcement worked, measured against nature's design? What are the benchmarks?
Well, you evaluate it based on 3 main things, really. First, bite strength. Does it feel solid? Are there any signs of cracking, chipping, sensitivity under heavy biting? Second, occlusal rim integrity. How well is the edge holding up? Is the seal intact? Is the surrounding tooth structure protected?
Makes sense.
And third
is cuspal strength.
Ah,
How well are those individual cusps, or the restored cusps, resisting those potentially damaging lateral forces we keep talking about?
right. So considering all this complexity, the way stress flows, the natural strength of that dome shape, those high forces, it does leave you with a kind of provocative thought, doesn't it?
It's that.
Knowing that taking away the height of contour for a crown leads to that huge 75% strength loss compared to maybe 35% for an onlay, how often are we really making the best long-term biological choice when we opt for maximum intervention like a full crown? It feels like this incredibly delicate balancing act.
It absolutely is. It's a constant, sophisticated dance between mechanical necessity, you have to make it strong enough, and the biological cost of achieving that strength. That's the heart of restorative dentistry.